Hello dear friends, I'm Mateus, and I'm going to present to you the paper Design of Ku-band Filters and Diplexers for a Heterodyne Transceiver using coupled open-loop resonator cells. This paper is a contribution from me, Eric Barbosa, and Sebastian Rondinet, all the three authors from the University of Brasilia. Microwave bandpass filters are of great relevance in the context of active radio frequency front ends, mainly in low noise block converters, block up converters, and in the interconnection between the transmitter and the receiver chains. These elements helps to avoid effects such LEO leakage, LEO self-mixing, the image problem, and improve the isolation between the transmitter and the receiver paths. Additionally, the demand for these devices is expected to grow up even more during the next decade due to the LEO satellite market growth during this decade. To be widely deployed, these devices must be low profile, low cost, and low power. The objective studied in this paper are the design of two bandpass filters, one for the receiver, operating from 11.7 to 12.2 GHz, and one for the transmitter, operating from 14 to 14.5 GHz. Additionally, a Diplexer is also proposed to be used in a transceiver heterodyne architecture. The area of application is on mobile SATCOM-to-move user terminals. The proposed solution makes use of coupled open-loop resonator filters, which makes use of right quality factor resonator. The technology of fabrication is over microstrip line PCBs. The basic resonator cell is a rough wavelength square open-loop resonator, and when a pair of this resonator are placed close enough, its phasing fields make them get coupled. This coupling could be quantified to design the filters. In Figure 1, we can observe the basic geometry of this resonator, and in Figure 4, we can observe 4 different types of coupling between these resonators. The design procedure of these filters consists basically in first, designing the low-pass prototype impedances, which is based on the type of the filter, a Chebyshev, a Butterworth, a Lipsky, or other. Then, we must determine the required external quality factor and the coupling coefficient matrix of each pair of resonators. Next, we must extract the physical dimensions of the resonators which is related to the coupling coefficient matrix. For this, we must use an electromagnetic solver software. And finally, we can proceed with an optimization process to improve the performance of the circuit. To design the Diplexer, we must also choose a power combiner. For this application, and for its simplicity, a quarter-wave matched tin junction was chosen by the authors. In Figure 4, we can observe the image of this power combiner and with its S-parameter curves. In Figure 5, we can observe the final geometry of the Diplexer. The viewer can also observe that there exists a 90-degree spacing angle between the receiver and the transmitter to improve the isolation between the chains. Due to small dimensions, this device presents a great sensibility to the manufacturing tolerances. Due to this, a microwave PCB standard must be obeyed to limit the fabrication errors. For this purpose, the IPC6018C was chosen, which states that the maximum allowed error is of 20.5 micrometers in the worst case. To verify if the devices are strong enough against these errors, a 250 trial Monte Carlo yield analysis was performed. In Figure 6, we can observe the bound limits of the simulation. The achieved yield was of 78%. In Figures 7, 8, and 9, we can observe a photography of the fabricated elements. We can observe that the resolution of the manufacturing process was very good, and the aspect ratio of the resonators are also very good. In Figure 10, 11, and 12, we can observe a comparison between the simulated and the measured S parameters of the filters. In solid lines, we have the measurements, and in the dashed lines, we have the simulations. We can observe that both the results agree with a good level acceptance, diverge just in 1.7 dB in the worst case. As a conclusion, we could list that while the devices had presented insertion loss better than minus 2.8 dB, reflection coefficient lower than minus 10 dB, and isolation greater than 20 dB in the worst case. Additionally, the use of the IPC6018C guarantees a reliability manufacturing process to fabricate right-selective devices. As a future work, we could list that yield optimization could be performed to improve the performance of the circuit, and that TRL could be performed to remove the nonlinearities of the measurements. Thank you for your attention, and now I'm open to questions.
Hi, my name is Vitor Almeida. I'm going to present the KU band metallic via through interconnect to strip-line transitions for non-standard PCB via setup using sequential build-up technology. I'm Vitor Almeida from the University of Brasilia. Matheus Santana, Eric Barbosa, and Sebastian Andino are also from the same university. The sequential build-up technology, the SBU, is one of the most common processes in printed circuit board manufacturing. It consists of pressing and gluing pairs of layers together, in which the drilling for the metallic view through interconnections are done before each press. And this implies some limitations on their combinations. Just to know the names here, the buried vias are the ones that connect just inner layers. The blind vias connect surface layers to inner layers, and the through-hole vias pass all through the PCB stack. Regarding those limitations, if we have here 3 setup examples, given that we already used those black vias here, we could not connect layers 3 to 4, for example, and in setup 2, we could not connect layers 4 to 8 because of these crossing terminations here. That's the problem. And in setup 3, you have this kind of limitation. The context of this paper is a project for Rotman lens interconnections, so we have some requirements. Those are, we have 4 strip line layers and individual channels, and we must maintain the relative position of the ports, and the phase delay must be equal for all the paths. It's easy to see here that this structure cannot be achieved using simple blind vias because of those crossing terminations. And if you use through-hole vias here, we would hit the strip line layer. So we came out with the solution of the capacitive MVTI. It consists of aligned vias terminated by circular plates, and since the layers are spaced by the prepreg, that is the glue, we have here a capacitive coupling. So the signal can be transmitted all through the PCB stack. And here we have, by this discretization, we have the combinations that we want. The implementation of this was done with an SMP connector connected to this via structure, and around them we have GND vias to ensure that the same potential is seen all through the via height, and we also avoid radiation leakage. The SMP connector also have some GND vias to have its impedance matched. And to connect the via through to the 50 ohm strip line, we must match the via impedance. So having a capacitive termination, we want to have an inductive session to cancel the imaginary part of the impedance. And having here a real impedance, we just use a quarter wave transformer to match it to the 50 ohm strip line. This chamfer here is really useful to adjust the impedance matching and the phase difference. And here's the whole structure for channels. And the PCB was manufactured. We have here a 5mm PCB given these materials. And here is a cut view of the manufacturer MVTI. We can see the thicker layers. Those are the substrate. The thinner layers is the prepeg, spacing the vias, spacing the plates. And we notice some misalignment between the layers. That is expected, but we have to analyze it. So it's estimated here a misalignment of 75 micrometers, which does not represent a great impact on the S parameters of the transitions. Given that we have a threshold here of reflection coefficient, we have a tolerance of 0.2 millimeters of misalignment, which is pretty much within the manufacturer's capabilities that in general can reach this misalignment at most. The measurements of the transition, the whole stack is presented here. The dashed line represents the simulations, and the solid lines represent the measurements. And we observe that we have a little more loss than expected, but the fact is they are uniform between the paths. This is really important for the application, so because it would not affect the array factor of the lens. And here we have the phase delay, the phase delay difference for all paths. So we have here the difference between the pairs, and we want as low as possible to ensure a good radiation pattern. And we have here these levels of 5 degree in average does not present a great impact on the array factor. And so we presented a workaround for technology limitations, bringing new combinations of connections allowed, with still the same industrial process. So there's no need for post procedures, and the serial production is still cheap. We also demonstrated that the system is robust for interlayer misalignment, giving reliability to the results and repeatability of the structure. For future reworks, we know that the solution can be used in several other applications, and less shielding vias may be used depending on the application and the requirements. And the transitions of the SMP connector may be exchanged because from case to case you use other type of connections, so they are independent of the via transitions. So thank you for your attention. This is my email. Feel free to send me any message. And now I'm open to questions.
Hi, I am Guilherme Félix de Andrade. electronic engineer and master's student in electrical engineering at UNB. My work presents a systemic analysis and measurements of heterodyne radio frequency front-end receiver for satellite communication in Ku band, and the design and characterization of single-stage low-noise amplifier. Satellite communication system has typically three network elements, as shown in the figure. A ground station, which provides the network and link completer configuration. A terminal that promotes the interface between the end user and the system, and a geostationary satellite that communicates between a ground station and terminal. In this work, a forward link is present. Receivers in satellite communication system have the purpose to demodulate the transmitter radio frequency signal information, processing it appropriately, providing a minimum noise figure and sufficient amplification for the original signal reconstruction. There is a trade-off between linearity, low noise figure, spectral efficiency, high gain, and low power consumption. And to balance these trade-offs required by the receiver was designed a heterodyne receiver with a double demodulation, adding IF frequency before baseband signal. Receiving this figure has been designed to operate in the entire band of 11.7 GHz to 12.2 GHz with 500 MHz bandwidth. The signal received is separated in TX and RX by a Diplexer, amplified by a low-noise amplifier cascade, filtered through an RF filter, and down-converted to IF frequency by the passive mixer. The heterodyne converter was defined in two stages, performing the conversion of the signal in RF from 11.95 GHz to around 3 GHz. For the transceiver down-converter the frequency to baseband. In the system view was used a WAT-EF tool to plan intermediate frequency in transceivers to avoid spurious band caused by the mixer and to identify frequency bands where spurious ones are irrelevant to the project. The intermediate frequency of 3 GHz was selected because it is free of spurious and it is the frequency range of the AD9363 transceiver and the oscillator selection. It is possible to identify frequency ranges where spurious are irrelevant to the project according to this figure. A system-level simulation of the topology receiver was made with the parameters of the inserted commercial activity components and the expected gains of the project passive components, described in the table. The printed circuit board was fabricated in Lauken. In this PCB, there was a transceiver composed by a transmitter and a receiver designed in this article. The substrate chosen for active radio frequency front-end project was Rogers AD250C with thickness of 0.508 millimeters due to the fact that its loss tangent and its permittivity are low, making its trails for a certain large impedance, consequently less sensitive to manufacturing process. The receiver was connected to signal generator in the input of Diplexer in range the input power. EF filter output was connected to spectrum analyzer to measure the power out according to the table. Active radio frequency front-end receiver PCB for vehicular satellite communication has been designed and characterized in this work, showing the gain of 40 dB in Ku band. The substrate chosen for LNA project was Rogers RO4350B with a thickness of 0.508 millimeters. The transistor selected was CE3512K2 because its performance. AM simulations were done in the Keysight Advanced Design System (ADS) with momentum simulation tools. First, a DC analysis was done and the optimum noise figure and gain performance are achieved with Vg equal 2 volts and the drain current 10 mA. To minimize the noise performance and increase its gains, the LNA input port has been matched to the minimum noise figure and in the output port matched to deliver maximum power, consequent high gain, utilizing transmission lines. LNA's common characterization, evaluating their performance through analysis of gain, noise figure, compression point, and input third-order interception point. In this study was measured on S parameters in vector network analyzer. A single-stage Ku-band LNA using transistor CE3512K2 was designed with 10 dB measured gain for future minimized cost of active radio frequency front-end PCB. Thank you very much.
Hello, my name is Vinicius and I'll be presenting the RF SP40 pin diode switch for mobile satellite communication system at KU band. Well, I'm from the University of Brasilia. I'm with Eric Walter and Sebastian Rondino, also from the University of Brasilia. Well, the first thing is to note that the switch itself is designed to compose a much bigger system of mobile satellite communication at Q-band. It also has a transceiver, Hartmann lens, and an antenna array. At the right side we can see the radiating system with the RF switch, the Hartmann lens, and the antenna array. Well, the main requirements for the design of the RF switch is it to be at the Ku band between 11.7 and 14.5 gigahertz. It must have a power handling of 33 dBm. It also has to be with 4 ports and has a low loss. Well, first thing, what is an RF switch? The RF switch is a control circuit, basically, which it directs the signal or the power flow from the main port through another selected port by changing the impedance at each port. At the right side, we have a single pole and through switch. N is due to the n number of ports which it can be selected. It was decided for this design to be in a PCB, in a printed circuit board with microstrip lines, so it has a low profile, an easy assembling, and in larger scale production it becomes lesser and lesser expensive. Well, there are two main types of control elements: the microelectromechanical systems, MEMS, or solid states like diodes or transistors. All simulations were held in Keysight's ADS, and the control element chosen was the pin diode due to its power handling. It has a much better power handling than the other solid states components. So the diode chosen was the MA4SPS 502 from Macon, and at this right side we have a simplified scheme of the control element, which when it's up, the key is up, it represents the on state. When it is directly biased, and when it's off, it represents the off state, which is reversely biased. So on reverse, we have it appears a capacitance here with also a series resistance. Well, the main topologies of this kind of circuit is with control elements in series or in parallel or both, which is the hybrid. In series, it relies more on the resistance in series, and in parallel it relies more on the capacitance when it is reversely biased. So it is much easier to obtain a better insertion loss. That's why the design was made with the parallel diodes. But it also has a disadvantage, which is the use of the quarter wavelength transmission line, which make the band narrower, make it more narrow band for the switch. Well, the substrate was the AD250C, which is made from PTFE and fiberglass. These are the main specifications. And the bias circuit was made with a double radial stub, and also it was used a series resistor here with 50 ohm to control more the currents in the diodes. Here are the results from the electromagnetic simulation. And well, here we have the single pole 4-through switch, the SP4T itself. It was made with a characteristic impedance of 50 ohms with SMD components, capacitors and resistors, with the diode that we just presented, and the biasing. Well, since the parallel is with a inverted logic, so with a minus 4 volts, we have an on state on the port, so it means that the diodes are not conducting the signal, and it can become from the port 1 to port 2. And if it has a bias of 1 volt, it means that the port is off, which concludes with the both diodes conducting the signal. And here we have a scheme of each branch is the same basically. So the common port, the output port, both DC blocks, preventing from the DC power to reaching the RF ports. Here we have the bias circuit that we just described, and the quarter wavelength microstrip lines between the diodes and the common port. On the right side we have the main circuit that was designed with the resistors, capacitors and diodes, and the bias for each branch or port. Well, since diodes are not linear components, we did use the large signal as parameter simulation that consider the compressing points of these elements. And at the left side we have the port 2 conducting on state, and all the other ports in off state, and the port 3 on state, and all the other ports at off state at the right side. So both of them are quite similar and present a insertion loss better than 2.3 dB. After that, it was held a yield analysis that is basically it is basically a parametric simulation to predict deviations from the manufacturing processes. So we had 250 iterations, and only 11 of them were below the target point that was 2.5 dB of insertion loss. Well, analyzing the results, we conclude that the insertion loss was approximately 2 dB. That is a good thing considering the band size and the number of channels. We also had a isolation better than 19 dB, which is really important for the pointing system to not have interference from ports that we don't want to. And we have also the yield analysis that give us more confidence that the circuit will work as expected. In conclusion, the SP4T design showed good results in power handling, insertion loss, isolation. It showed some robustness to possible deviations in manufacturing. Well, the next steps are manufacturing the circuit itself, assembling it, and after that also testing to verify that our conclusions are correct. These are the references that were used, and that's it. Thank you so much. Have a great day.